August 19, 1942. Dawn, Red Beach, Dieppe, France. The landing craft ramp crashes down onto the shingle beach. Corporal Dave Collins, a Canadian signals operator, leaps into the surf, clutching his heavy, invaluable wireless set, the number 18 radio pack. He stumbles, the pack sinking momentarily beneath the water before he regains his footing. He scrambles to cover, frantically trying to contact his command. The radio crackles, spits static, and then falls silent. The water has infiltrated the delicate components. Dave shouts in frustration, realizing he is now deaf and mute. The entire massive coordinated assault is unraveling around him, silently drowned by a few inches of seawater. The Dieppe raid of August 1942 remains one of the most brutal and strategically intricate failures of the Allied forces during World War II, codenamed Operation Jubilee. The raid was intended as a reconnaissance in force, a proving ground for Allied landing techniques in German coastal defenses. Instead, it became a tragic, bloody massacre, costing thousands of Canadian lives and providing the Allies with a devastating lesson. While military historians often focus on the shortcomings of armored support and air cover, one of the most critical and overlooked failures of the Dieppe raid was the catastrophic collapse of wireless communication. This was the silent killer that ensured the disaster. Modern warfare, even by 1942 standards, depended entirely on reliable radio communication. Coordinated assaults required constant real-time contact between landing units, between ground forces and naval command, and between command structures and supporting artillery. Without it, the modern battlefield instantly reverted to the chaos and isolation of the 19th century. At Dieppe, the communication system failed almost entirely from the moment troops hit the beach. The primary reason was simple yet devastating: water. The landing craft encountered heavy surf and often came under fire, forcing rapid deployment into deeper water. The heavy, cumbersome radio sets, the lifelines of the assault, were frequently submerged, even briefly. The Allied radios of the era were not designed to be waterproof. They were protected only by thin metal casings and basic rubber gaskets, which were easily compromised by the impact of landing or the pressure of water. The consequences of this communication failure were immediate and catastrophic: lost coordination. Units landing on different beaches were unable to inform each other that German defenses were overwhelmingly strong, preventing coordinated withdrawal or effective support. Delayed orders meant command ships offshore were unaware of the devastation on the beach, continuing to send follow-on waves into a fortified death trap. No fire support. Ground units could not accurately direct naval gunfire or airstrikes onto German strongpoints, leaving the infantry exposed to relentless machine gun and mortar fire. Corporal Collins' experience, the sputter and death of his vital wireless set, was replicated across the entire beachhead. The enemy was not just the German machine guns, the enemy was the simple, unstoppable force of the sea. After the raid, the technical post-mortem was grim. While the Germans had demonstrated superior tactical defense, the Allies themselves had committed a logistical and engineering error that magnified their losses tenfold. It was determined that the fragility of the radio sets to common battlefield hazards, water, mud, and physical shock, made them dangerously unreliable. The focus of the Allied war effort shifted immediately to solving this communications crisis. The challenge was passed to the scientists and engineers of the Allied nations, with a specific and intense focus on Canada. Canada had already distinguished itself as a major industrial power, mass-producing equipment including its own versions of key military radios like the wireless set number 19, intended to provide vital armored infantry communication. The Canadian scientific community was tasked with an urgent, singular goal: develop a material or technique that would render these essential military radios completely waterproof. The requirements were impossible. The sealant had to be flexible, durable, easily applied in factory settings, and capable of withstanding the immense shock of artillery fire and rough handling. Military planners were seeking a simple solution: a better gasket, an improved rubber seal, or an enhanced wax dipping process. What the Canadian scientists were about to discover, however, was not the simple sealant they sought. Their relentless, often frustrating experiments with new synthetic materials and plastics, initially viewed as failures, would lead them entirely by accident to a profound technological breakthrough. They were about to stumble upon an engineering concept that would not only waterproof existing radios but fundamentally transform them into a new class of unbreakable secret weapons, solving the DWII communication failure once and for all. Late 1942, National Research Council, NRC, Laboratories, Ottawa, Canada. Dr. Eleanor Vance, a young Canadian chemist, wears thick protective gloves as she works with a new polymer compound. Her workbench is littered with failed experiments, seals that cracked, rubber gaskets that disintegrated in salt water, and waxes that melted under heat. She sighs, tossing a sample into the trash. "Another failure," she mutters. "The military wants a perfect sealant to waterproof the radios, but everything we try is too brittle or too weak." Just then, a clumsy assistant knocks over a beaker of liquid plasticizing agent onto a nearby radio component. Vance stares at the part, now encased in a thick, clear material. A light bulb goes off. Wait a minute, not a seal, an armor. The catastrophic communication failure at Dieppe, where water intrusion rendered vital radios silent, forced the Canadian scientific establishment into immediate, high-pressure action. The mission handed to the NRC of Canada was straightforward: solve the problem of water damage to sensitive electronic components, particularly those in the critical wireless sector, the number 19 set, primarily used by Canadian and British armored units. The initial approach, guided by conventional military engineering wisdom, focused entirely on sealants. Scientists like Dr. Vance spent grueling months attempting to create a flexible, durable, and chemically inert material to serve as a gasket or sealant to physically prevent water from entering the radio casing. They experimented with new synthetic rubbers, various waxes, and complex composite materials. The goal was to find a substance that could endure the shock of artillery, the abrasive nature of sand, and the corrosive effect of salt water while maintaining its sealing integrity. These attempts were almost universally failures. The problem was fundamental. In combat, the radio casing itself would warp under the shock of explosions or rough handling. No matter how robust the sealant, the casing would fail, and water would inevitably penetrate the delicate vacuum tubes, resistors, and capacitors. The pressure of solving the crisis mounted as the Allies planned the eventual invasion of Europe, knowing that another Dieppe-style communication failure would be catastrophic. It was during this phase of repeated frustration and failure that a profound scientific pivot occurred, an accidental discovery born from a discarded material and a basic engineering insight. Canadian researchers, working extensively with new plasticizing agents based on synthetic resins developed rapidly during the war, realized the potential of a discarded liquid polyester resin compound. Unlike rubber or wax, this resin, when mixed with a catalyst and exposed to heat, underwent polymerization, turning from a thick liquid into an incredibly hard, dense, and physically stable solid. The realization was this: the problem wasn't the casing, it was the components. Instead of sealing the casing around the components, why not encase the components themselves? If the delicate, vulnerable parts, the coils, transformers, and wiring junctions, could be entirely submerged and cured within an insulating solid block of plastic, they would become completely impervious to water. Furthermore, the resulting solid block would be fixed in place, making the components highly shock-resistant. This was a radical, almost heretical idea in electronics. Conventional wisdom dictated that components needed airflow for cooling and accessibility for repair. The Canadian method of potting or casting components in plastic eliminated both airflow and accessibility. It was a shortcoming of the original objective, finding a flexible seal, that led to the success of an entirely new principle, creating a rigid, unbreakable internal framework. The challenge now shifted from chemistry to industrial engineering, the plastic formula. They needed to refine a resin mixture that would cure without warping or damaging the delicate wiring and would remain chemically stable across the extreme temperature ranges of European and North African warfare. On a manufacturing scale, they had to devise a mass production method for submerging thousands of individual components, each unit requiring a precisely measured dose of resin and catalyst and curing them rapidly enough to meet the enormous wartime demand for radios. The unbreakable principle: the final cured plastic block had to be strong enough to endure the shock of a nearby artillery shell without cracking or transmitting the force to the fragile components embedded inside. The Canadian scientists demonstrated that the fully cast components were effective. They produced small modules, circuit assemblies cast entirely in the thick, clear plastic block. These blocks underwent rigorous military testing, often involving being submerged in salt water for days, tossed from moving trucks, and even exposed to explosions. The result was remarkable. The cast components remained fully operational, utterly impervious to water and shock. The plastic effectively became a permanent, unbreakable armor for the radio's most vulnerable parts. This accidental breakthrough, the shift from a flexible sealant to rigid cast armor, was immediately implemented in the Canadian-built radios, transforming them from fragile communication tools into robust, unbreakable secret weapons. The failure to find a perfect seal had generated a revolutionary new method of safeguarding electronics, a technique that ensured communication, the lifeblood of coordinated attacks, would never again fail due to water. By early 1943, at the RCA Victor manufacturing plant in Montreal, Canada, foreman George Davis supervised a production line that seemed entirely alien to a conventional electronics factory. Instead of delicate hand soldering components, automated machinery poured thick, clear liquid resin into molds containing radio parts. The air was warm and smelled faintly of chemicals. A visiting British major observed a cured block of components being removed, a pristine solid plastic brick with wires embedded inside. The major picked up the block, tapped it, and shook his head in disbelief. "It's cheating, Davis. It's supposed to be delicate. This is an armor-plated circuit board." The accidental discovery at the Canadian National Research Council (NRC) labs, the realization that potting components in plastic resin was superior to merely sealing the casing, ignited a massive, urgent industrial retooling effort across Canada. The Canadian military industry, already a powerhouse in producing vehicles and munitions, now faced the challenge of pioneering a brand new field: mass-produced plastic-armored electronics. The primary recipient of this revolutionary technology was the wireless set number 19. The critical radio used by Allied armor and infantry. The wireless set number 19 was an advanced radio for its era, providing essential high-frequency communication between tank crews, infantry support, and command units. It was, however, notoriously vulnerable to the two most common killers of battlefield electronics: water and vibration shock. The DEP raid had revealed the water vulnerability, and the constant jarring and artillery shock experienced inside a moving tank guaranteed frequent mechanical failures. The Canadian casting technique, known as potting or encapsulation, solved both problems simultaneously and fundamentally. Waterproofing was redefined by submerging and permanently encasing key components, such as transformers, coils, resistors, and delicate wiring junctions, in a solid block of cured plastic resin. The Canadians achieved absolute waterproof integrity. Water could still penetrate the main radio casing, but it could no longer reach the vital electronics, as they were protected within their own impervious chemical armor. This meant a radio could be dropped into a river, removed, and once the external casing was drained, remain fully operational. Perhaps the most significant benefit was shock resistance. In a conventional radio, components were secured only by their solid connections and mounting screws, leaving them prone to microscopic cracking or bending from constant vibration, such as a tank traversing rough terrain or the massive pressure wave from a nearby artillery explosion. When cast in rigid plastic, the components were held in a fixed solid matrix. The plastic absorbed and distributed the shock, preventing the components from vibrating or moving, effectively making the circuit mechanically unbreakable under combat conditions. This technology transformed the Canadian wireless set number 19 into a true secret weapon. Initial production was challenging and complex. The Canadian factories, notably the large RCA Victor plant in Montreal, had to rapidly adapt to managing the messy chemical process. They devised automated pouring systems, developed precise temperature controls to manage the exothermic curing process, and designed specialized molds for the various component sizes. They perfected the process of using silica fillers in the resin to minimize shrinkage and thermal expansion, ensuring the fragile internal wires were not stressed as the plastic cured. The result of this industrial effort was the mass production of radio sets with essential internal components that were functionally immune to the traditional causes of battlefield failure. This gave the Canadian and British forces a tremendous unseen advantage as they prepared for the next unavoidable amphibious landings. Military engineers who were initially doubtful became immediate converts. Field tests carried out by Allied ordnance teams were harsh but conclusive. They immersed the potted radio components in vats of corrosive saltwater. they dropped the components from tall towers. Most remarkably, they positioned the cast modules directly near demolition charges, while the plastic block itself might display scratches or minor cosmetic damage. The electronic components inside remained flawlessly operational. The unbreakable designation was well-deserved. The profound strategic realization was that this innovation was not just about saving radios. It was about preserving lives and maintaining momentum. The failures at DEP demonstrated that an attack could only succeed if communication remained intact. With the plastic-potted Canadian radios, the Allied High Command now possessed the confidence to launch massive complex amphibious operations, knowing that the infantry and armored units hitting the beach would not immediately lose contact with their command structure or supporting fire. The deployment of this technique was immediately prioritized for all Allied forces using the wireless set number 19, acknowledging its critical strategic value. The Canadian invention born from a failed experiment and honed by industrial ingenuity provided the technological backbone essential to support the impending large-scale invasions of Europe and Italy. It ensured that the communication link, the lifeblood of modern combined arms warfare, would finally be as resilient as the soldiers carrying it. June 6, 1944. 8:30 a.m. Juno Beach, Normandy, France. The Canadian M4 Sherman tank, its turret tilting slightly from shrapnel damage, sits immobilized in the surf line. The seawater washes over the tracks. Inside the tank, a signals operator, Sergeant Michael McRiley, frantically attempts to raise his command. The external antennas are broken. The tank is flooded. Yet the radio, the rugged Canadian-made wireless set number 19, emits a clear, strong signal. Mick shouts into the microphone, directing the fire of the landing craft offshore. The connection holds. The communication holds. The failures of DEP are avenged by the simple, unbreakable plastic armor of a Canadian invention. The D-Day landings in June 1944 were the ultimate validation of Canada's failed plastic experiment. The massive synchronized amphibious assault on the beaches of Normandy was an infinitely more intricate operation than the disastrous raid on Dieppe. The success of the invasion, the most crucial military action of the 20th century, depended entirely on communication cohesion. If the radios failed in Normandy, as they had in Dieppe, the invasion would likely have been thrown back into the sea. The reliability of the Canadian potted wireless set number 19, and other Allied equipment using this encapsulation method, proved to be a quiet but decisive strategic advantage. The invasion force faced heavy surf, continuous enemy fire, and the brutal shock of naval artillery. Yet, communication channels remained steadfast, largely thanks to the impervious, shock-resistant internal armor provided by the Canadian plastic casting. The failure of German communications during the defense of Normandy, often due to artillery shock and moisture, contrasted sharply with the robust continuous network maintained by the Allies. This asymmetrical communication reliability allowed Allied commanders to maintain synchronization. Armored units, infantry, and engineers could operate as a cohesive whole, sharing real-time intelligence on enemy positions and avoiding the devastating isolation that plagued the DEP raid, while rapidly adjusting fire. Ground teams, often riding in heavily armored kangaroos, could instantly call in air and naval support, confident that their radio signals would penetrate the chaos, ensuring rapid and accurate responses to German counterattacks and preserving the command structure. Establishing secure beachheads required continuous contact between frontline units and command ships. The failure of a single critical command radio could have triggered cascading tactical consequences. The Canadian innovation provided an essential layer of redundancy against this catastrophic risk. Military planners realized the truth: the wireless set number 19 was not just a radio. It was a force multiplier. It gave commanders the confidence to advance their attacks and rely on logistical and fire support, ensuring that the momentum of the invasion was never again stifled by a silent communication failure. The unbreakable plastic effectively became the technological guarantor of the combined arms doctrine. The ultimate strategic impact was not measured in sunk ships or destroyed tanks, but in lives saved and time gained. Every time a radio held its signal when a standard set would have failed, a critical piece of intelligence was transmitted, an artillery strike was cancelled, or an ambush avoided. The reliability of communication reduced the chaos of the battlefield, saving countless soldiers who might otherwise have become casualties of miscoordination. The technology proved so effective during the initial landings that its application rapidly expanded across other critical Allied communications equipment, cementing the Canadian industrial establishment's reputation as a pioneer in military electronics. Initial skepticism and dismissals from engineers who preferred conventional seals were silenced by the undeniable success of the method in the field. The Canadian Army, once regarded as inexperienced in electronics, had provided essential technological security for the entire Western Alliance. The story of Canada's failed experiment that led to the unbreakable radio is a powerful testament to the fact that innovation often emerges from the crucible of military necessity and accidental discovery. This silent secret weapon, born from plastic resin, was crucial to the success of D-Day and the ultimate victory in Europe. The soldiers who relied on the unbreakable signal from their wireless set number 19 in the chaotic surf of Normandy were the first beneficiaries of a technological legacy that continues to shape our modern electronic world. Communication protected by plastic was, in every sense, the true victory.